Hello and welcome to our lesson on powers of complex numbers. So when we're talking about powers of complex numbers, we are talking about taking a complex number, whether it's in rectangular form or polar form, and raising it to a power. Now, just like raising any number to a power, what we're doing is repeated multiplication. So raising a number to a positive integer power is what we're going to focus on here. A positive integer power, again, it's just a repeated process, a repeated multiplication process, or a repeated application of our product rule. And we talked about that one in terms of our polar numbers in our previous topic. So we're going to be using the product rule multiple times here, and we're going to start by taking an example and squaring it. So we're going to do a little investigation here. Now, squaring any number or any expression doesn't really require fancy theorems because, we're just multiplying or using our product rule once. But as the power gets larger, and again, as we start to look at complex numbers in both polar and rectangular form, it's going to be helpful to be able to streamline. So if we can find some patterns and make a theorem or realize the theorem, then that's going to be helpful for us long term. So let's do a little investigation. Let's see if we can't just apply our product rule to the few problems I have here and come up with a theorem, a pattern. So first one, we have 2 cosine of 30 degrees plus I sine of 30 degrees, and we want to square it. Well, I'm going to abbreviate this. I like the compact form a little better. So what we're looking at is 2 cis 30, and we want to square that. So we're going to take that 2 cis 30, and we're going to multiply it by itself. So 2 cis 30. And now again, we can apply our product rule. Our product rule says all we have to do is multiply these absolute values. So we have a product of 4, and then we're going to add our angles. Oh, I do not like the pink. We're going to add our angles, so the 30 there and the 30 there means we're looking at 60. So our product becomes 4 cis 60 degrees. Okay, so not so bad. What about if we take this same thing, 2 times the cosine of 30 plus I times the sine of 30, but raise it to the third power? Well, to the third power means we can just take the squared, right? And then if I had an x squared and I multiplied it by an x to the first, then I would have my x to the third. So I can literally take the result, multiply it by another factor of itself, and get to that x to the third power. So that's what I'm going to do. I'm going to take the previous. We said 4 cis 60. That's what we just got. We're going to take that and multiply by another factor of itself. So now I'm going to multiply by another 2 cis 30. So what happens is we end up with, again, a product of our absolute values. So the 4 times the 2 is going to give us an 8. And then we're going to find the sum of the angles. And so the 60 here plus the 30 here gives us 90. And so we end up with 8 cis 90 on this one. Okay, and now we're going to take the same thing and raise it to the fourth power. So again, I had an x squared, something squared. I multiplied by itself to get that x cubed. Well, now I take that x cubed and multiply by a factor of itself, and that would take me to an x to the fourth. So if I can take what I have here, that's the cubed version, multiply by another factor, I'll get the fourth version, the fourth factor, to the fourth power. So I'm going to take my 8 cis 90 and multiply it by another factor of itself. What have I not used? Green. So let me multiply, oops, forgot to put my parentheses. Let me multiply by, again, 2 cis 30. So we're going to do this, and again, multiply those absolute values. So the 8 times the 2 is going to give us a 16. And then we're going to add our angles. And so we add our angles. We have the 90 plus the 30. That gives us 120. And maybe you're seeing some patterns forming. I hope you are, because on the next one, we're going to be jumping to the 8th power of this complex number. What's going to happen on the 8th power? If you can see it, it's pretty awesome. Go ahead and jump to that answer, but what could we do to jump, or where are the patterns happening? I wish if we were in class, I'd be like, just put your pencils down, let's talk this out. But maybe you can see it already. So let's look at what we started with compared to what the answer is in our problem. So here we started with, let me change colors here. We started with a square. So let's compare that, or let's look at the square and compare it with the absolute value and the angle that we're looking at. Okay? So if I look at the connection between the absolute value in the square and the argument and the square, or the radius in the square and the angle and the square, so 2 squared is going to get me the 4 that's here, and 2 times the 30 is going to get me the 60 here. Okay? And the same thing happens on this one. So if I look at the cube form, right, take the radius of 2 and cube it, and I get to 8. Take the angle of 30 and not cube it, but multiply it by 3, and I get to 90. Okay, take the radius here and raise it to the 4th power, I get 16. Take the 30 here and multiply it by 4, and I get 120. And it should really make sense that that's what's happening, because, let me back this up a little bit, when we are multiplying this thing by itself, right, that's what it means to square that, of course we're going to end up squaring that radius or that coefficient. And then if I multiply it again by a factor of itself, now we're cubing it. And again by a factor of itself, now we're raising it to the 4th power. I was going to say we're fourthing it, raising it to the 4th power. But what's happening with the angles is slightly different, because the angles, we're adding those each time we multiply. So each time we multiply, we add a 30, right? So the first time I multiplied, it was the power of 2, I had to add a 30. So that was 2 factors of 30. And then it was the power of 3, I had to add another factor of 30. So if it was the power of 4, I had to add another factor of 30. Well, repeated addition is just multiplication. So I could have said, instead of 30 plus 30, 2 times 30, right? Or instead of 30 plus 30 plus 30, that would have been 3 times 30. And again, instead of 30 plus 30 plus 30 plus 30, 4 times 30. Okay? And so looking here, while I could take my 4th power, so like if I had x to the 4th power and I could square that result, right, then that would give me an 8 altogether. I could have taken this thing and squared it, multiplied by itself, and got to this answer. I see the patterns. So let me use the pattern, right? If I have, get another color here. This is 2 cis 30. If I'm going to raise that to the 8th power, what I'm actually going to raise to the 8th power is going to be the radius length. So the 2 is going to be raised to the 8th power. And that would be cis of, here we're going to be multiplying, because we're going to be adding 8, we're going to be adding 30 to itself 8 times. So 8 times 30 is going to be our angle, 8 times 30 degrees. So the result, 2 to the 8th power, that's a lot. Let me just use the calculator so I don't goof that up. 2 to the 8th power is 256. So 256. And then we're going to have cis 8 times 30, which is going to make 240 degrees. Okay, so if we were to generalize this, we would say, here, for instance, if it's the nth power, no matter what that power is, the radius will be raised to that power, and the angle will be multiplied by that power. So we could say this would be 2 to the nth power times the cosine of n times 30 degrees plus I times the sine of n times 30 degrees, or the compact form 2 to the nth power, and then cis n times 30 degrees. and 30 degrees N and 30, whichever way. It doesn't really look nice either way, but that's what it is. Okay, so De Moivre is a French mathematician who actually has proven what we just showed there, the patterns that we just sort of discovered on our own. So his theorem says exactly what we just said. If you are raising a complex number in that trig form to a power, and really this applies to any real number, but we're going to be focusing on positive integer powers, that we're going to take the absolute value, take our radius length, and raise it to that power. That's what we see happening here. And we're going to take the angle and multiply it by that power, and that's what we're going to see happening here. Okay, or the condensed form shows the same thing. So we're going to raise this to a power here, and we're going to multiply here. Okay, so in short, if you're raising a complex number in polar form to a power, we're going to raise the absolute value, remember that's the radius, to the power of n, whatever n is, and we're going to multiply the argument by n, whatever that nth power is. Okay? And the argument, remember, that represents the, oops, this is radius, and this argument represents the angle. So you're going to raise your absolute value, raise your radius to the power, and multiply your argument, multiply your angle by that power. Okay? So pretty basic, and hopefully that makes sense also. I tried to show you last time the connection between exponent rules and the product and quotient rules. Maybe you don't need to write this, but just to clarify what I'm saying. Actually, let me do this over here. We said, okay, if we had like 2x to the 5th, and we were, so 5, and we were going to multiply by 3x to the 4th, that the multiply happens with the coefficients, so we get 6 there, but we actually add our exponents, and so we'd have x to the 9th. So the same with complex numbers when we're multiplying, right? We said multiply the radius lengths and add the angle. So multiply and add, connect. And then here with exponents, we had like 10x to the 7th, and then we're dividing by 5x to the 3rd. So the division happens with those coefficients. 10 divided by 5 makes 2, and then we subtract those exponents, so we'd get a 4. Same thing with our complex numbers, right? We would divide the radius lengths and then subtract the angles. Well, with exponents, if we had something like 3x to the 4th being cubed, we would cube the coefficient, so our coefficient here would be 27, and we would multiply the exponents here, and that would give us x to the 12th. So it's the same thing. This is multiply and add, right? This is divide and subtract, and this is raise our coefficient to our power and then multiply our exponents. So we raise our radius to a power and we multiply the angles. Okay, it's the same operations that we connect in terms of powers and exponents and actually logarithms. We connect those here. Okay, so let's try to apply our theorem. Let's say that z is this complex number with the radius of 5 and an angle of 60 degrees, and we want to find, in this case, z cubed. So if I have to cube this, I'm going to write the compact form. I like that better. I have 5 cis 60, and I want to cube it. So again, I want to cube the 5, so 5 is going to be cubed, and then I want to multiply my angle by that power, so 3 times my angle, which means I'm looking at 5 cubed is 125, and then it's going to be 6 cis 3 times 60, which is 180 degrees. Or if you wanted to have the expanded form, you have 125 and then cosine of 180 plus I times the sine of 180. And we've done it. So we don't have to do any fancy actually multiplying something by itself 3 times, multiply our angle,
raise our coefficient, raise our radius, our absolute value to the power, and we're good to go. Sometimes we need to take that and convert to rectangular form, so that's what we're going to see in the next one. We already have this thing condensed. Once we have it condensed again, we're going to take it to rectangular form. So this one, again, this is already in compact or condensed form, so we're good. We're going to take our radical 10 and raise it to the 6th power. And then we're going to take our angle n, multiply it by 6. Now, radical 10 to the 6th power might look a little strange, and you could probably just put that in the calculator, but I want to try to avoid that if we can, because it's actually going to end up being a nice number, but sometimes it's not. We want to keep our exact form, and really it's just something we should be able to handle. So if you recall from your algebra days, the square root of 10 is the same thing as 10 to the 1/2 power. That's what we are raising to the 6th. And then we have cis over here. 85 times 6 would be 500. I don't even. It's too late at night for me to be trying to multiply. Yeah, 510. Okay, I can still multiply. So this is going to be 510 degrees here. And then this, just like we were doing, this is a product here. So I have half of 6, which means this is really 10 to the 3rd for our radius. So 10 to the 3rd, cis 510. And 10 to the 3rd is 1,000. So we're looking at 1,000. And then because I want to actually convert this to rectangular form, I'm going to expand this out and then evaluate. So it's 1,000 and then cosine of 510 plus I times the sine of 510. And now, again, we want to take it to rectangular form, so I have to evaluate this. So we're going to be looking at, let me change colors here, 1,000 times, we have to figure out the cosine of 510. Now 510 is not explicitly on our unit circle, but we can find a coterminal angle and see if it is, right? So remember, we can always add and subtract factors of 360 to get coterminal angles. So if I took 510 degrees and subtracted out 360 degrees, I just can't. We're looking at 150 degrees. I feel so insecure in my math work right now because it's late. Yeah, it's 150 degrees. So this is the same as the cosine of 150. If you like that better, it's a coterminal angle, so it's the same. So I can write 150 degrees there instead. So at 150 degrees, we're looking at 150 degrees would be in quadrant 2. That's a 30 degree, oh my eraser, a 30 degree reference angle. So at 30 degrees, we're intersecting the unit circle at radical 3 over 2 and 1 over 2, but in quadrant 2 we're negative. So the cosine of 150 is going to be negative radical 3 over 2, plus the sine at 150 is going to be a positive 1/2. And those just need to be multiplied by 1,000. And so final answer, rectangular form. When we multiply here, 1,000 divided by 2 makes 500, so this would be a negative 500 in front of our radical 3. And then when we multiply here, half of 1,000 again is going to be 500. This time it's positive, and that's our coefficient of I. So that's the rectangular form of radical 10 cis 85 to the 6th power. Okay, so not awful. Because of De Moivre's theorem. I have a really hard time saying that. It's a tough French name. So this guy's theorem. How about that? Okay, now in trig form, we can see how this is a shortcut for our work, but it's also going to help us when we're trying to raise complex numbers in rectangular form to powers. For example, if I wanted to find I, or 1 plus I radical 3 to the 8th power, and have an answer in that same rectangular form that we're given, I don't want to take that binomial and multiply it by itself 8 times. That would be a bit insane. So what we're going to do is make this a polar form so that we can apply our theorem and then convert it back to rectangular form. So if I wanted to take this complex number, which right now is in terms of x and y, right? Here we can see that x is 1 and that y is radical 3. We know our x and y components. We can use those to find the r and theta to write our polar form. So we know that r, or hopefully we remember that r is the square root of x squared and y squared. So 1 squared is 1, radical 3 squared is 3, 1 and 3 makes 4, so we have the square root of 4, which makes our radius 2. And then our theta is the inverse tangent of y over x, so radical 3 over 1. So radical 3 over 1, remember we're looking for an angle where we end up with a radical 3 on the top and a 1 on the bottom. And remember, these are coordinates. In our coordinates, all these radicals are over 2. So this is our sine, or our y. This is our cosine. And that means we're looking for a coordinate that is 1/2 and then radical 3 over 2. And it's in quadrant 1. Everything is positive here. So that's going to happen at 60 degrees. So that means our theta is going to be 60 degrees. Or pi over 6 radians, since it doesn't specify it, and we're going to end up going back to rectangular form. I don't think it matters, so I'm going to stick with the 60 degrees. Okay? That means that the polar form for our complex number is going to be, remember, r cis theta. So the polar form becomes 2 cis 60 degrees. And what we want to do is take that and raise it to the, up here, 8th power. So when I raise this to the 8th power, it's actually raising the radius to the 8th power, and it's multiplying our angle by 8. And that's going to make it 2 to the 8th, I feel like I did that one. Yeah, 256 here. And then we have 480 degrees here. Okay, now that's the polar form. Since we want rectangular form, I'm actually going to expand this out. So if I expand this out, it's 256. And then cosine of 480 plus I sine of 480, and then again evaluate this to get that rectangular form. So 480, again 480 is not explicitly on our unit circle, so I'm going to subtract 360 to get a coterminal angle that will hopefully be there. Yep, that's going to be 120 degrees. So this is the same as 120 degrees if we would prefer to see it in that form. In any case, I have to evaluate. So I am going to be looking at 256 times at 120. So let me draw this out. And if you have your unit circle, then obviously this is pretty straightforward. 120 degrees, I'm just trying to go green here. 120 degrees, that's in quadrant 2 with a 60 degree reference angle. So 60 degrees intersects the unit circle at 1/2 and radical 3 over 2. In quadrant 2, cosine's negative, x is negative. So the cosine for 120 is a negative 1/2. Plus we have I times the sine of 120, which is our radical 3 over 2. And those now just need to be multiplied by 256. So half of 256, or why did I do that? 256 divided by 2 is 128. So I'm looking at a negative 128. Plus, again, we're going to, when we multiply here, end up dividing the 256 by 2. So I'm going to have 128, and I have a factor of I in there, and I have a radical 3 in there. And that's going to be the rectangular form of that complex number, 1 plus I radical 3 raised to the 8th power. Okay? Much better. Maybe still, a decent or a fair amount of work, but not overly difficult work. And I promise you the work that we did there is much easier than actually taking that binomial and multiplying it out by itself 8 times. Okay? Let's try that again. So we're going to take this and make it a complex number. Again, they're giving us our x and y components. X is radical 2 over 2. Y is a negative radical 2 over 2. So our radius is the square root of radical 2 over 2 squared and negative radical 2 over 2 squared. So in this case, let's see. When I square radical 2 over 2, I square this, I'm going to get 2. And I square the bottom, I'm going to get 4, so that's 2/4. I'm going to get the same thing there, 2/4 and 2/4. Well, that's going to make 4/4, which is 1, and the square root of 1 is 1. So we're looking at a radius length of 1, and our angle is going to be the inverse tangent of that that y value, negative radical 2 over 2, divided by that x value, radical 2 over 2. Well, that's an easy one to find on the unit circle because it hasn't been simplified at all. And so where do we have a coordinate where our x is radical 2 over 2 and our y is negative radical 2 over 2? So that's going to be which quadrant? Where we have positive x and negative y. That's quadrant 4. So in quadrant 4, the 45-degree reference angle in quadrant 4 is 315 degrees. So my angle, oops, this was supposed to be, did I do that over here too? No, I did. Okay, inverse tangent. Our angle is going to be 315 degrees. All right, so now we know that we are looking at the complex number in polar form. We're looking at r cis theta, so 1 and then cis 315 degrees. We're raising that to the 8th power. So we want to take the 1 and raise it to the 8th power, which obviously is going to be 1. And then we want to take the 8 and multiply it by the 315. So 1 to the 8th is just going to be a 1 here. So I don't really need the 1. I'm just going to focus on the cis. 8 times 315. 8 times 315, which is 2,520 degrees. Now again, I want the rectangular form of this one, so I'm going to expand this out. So this is 1, which we don't need. Cosine of 2,520 plus I times the sine of 2,520, and we got to figure out where in the world that is. So I'm going to take my 2,520, and I'm going to keep subtracting out 360 till I find a coterminal angle that is explicitly on my unit circle. So I'm going to have to subtract out a bunch. Let's just keep going until we land on the unit circle. And boom, I'm on 360. So this is the same as 360 degrees. That's a coterminal angle. So same as 360 if you want to look at it that way, which means we're looking at a quadrantal angle, right? Where a full complete rotation, we're landing on the positive part of the x-axis. So what's the cosine at 360, which is the same as the cosine at 0? That's going to be 1. So this ends up being 1 here, plus we have I times the sine at 360. Well, the sine at 360, that y value is going to be 0. So if we multiply anything by 0, that part goes away, which means this whole thing is equal to 1. Okay? So we end up with a real number for that complex number raised to the 8th power, which I know it's a little mind-blowing to see it all, but it is what it is. Okay, so sometimes we work, and we've seen this happen before, right? So we end up with a complex number that has both components, but sometimes one of them ends up going away like it did here. The imaginary part canceled, and sometimes the real component's going to go away and you just have the imaginary left. So be prepared for all situations. Now, this is a point where I would say pause the video and give the last one a try. Otherwise, let's go about our business here. Let's try to figure out from our x component of -2 and our y component of -2 what the radius and angle is so that we can take the polar form and raise it to the 5th power. So we know that r is going to be the square root of -2 squared plus -2 squared So we have 4 and 4, which is going to make 8. And radical 8 is not exact, but it does simplify, so we really should be simplifying. Some of you in your homework, I didn't mark you off for that, but technically you should. So we're going to make this 2 radical 2, and then we're going to find our theta, which is the inverse tangent of negative 2 over negative 2. That ends up being inverse tangent of 1. So where do we have an angle? An angle where the inverse tangent is, it's a positive 1, but I don't want to ignore those negatives, right? Because I want to make sure that I'm finding my angle in quadrant 3. But where do we end up with 1? A tangent of 1, but in quadrant 3, that's going to be at our 45-degree reference angle. So again, just picture this, right? In quadrant 3, our 225-degree angle, it's going to intersect the unit circle at radical 2 over 2, radical 2 over 2, both negative. So when I divide this y value by this x value, I end up with that tangent of 1. Okay? And so this, theta, is going to be, again, the 45-degree reference angle in quadrant 3, which means theta is going to be 225 degrees. So now I have r and theta, which means this can be rewritten. We're looking at r, which is 2 radical 2, cis 225 degrees, and I'm raising this to the 5th power. So I'm going to take the 2 radical 2 and raise it to the 5th power. Now I'm wondering if I should have left the radical 8. Huh. Alright, I'll leave that alone. And then we have the cis. It's going to be 5 times 225 degrees. And so let's figure this out here. I don't know if there's going to be a good two. Yeah, the radical part is going to be a little ugly. I feel like I'm possibly doing something wrong in this problem. You're probably screaming at me like, I just took this problem out of a book, so like, did I copy the problem wrong? Did I make a mistake? Just bear with me. like you have a choice. You've probably already turned the video off, so I'm likely talking to myself at the moment. But it is fine. I want to find this problem that I copied, possibly incorrectly. Or maybe I'm doing this right, and it's just an ugly problem. And then I'm really going to hope I didn't assign an ugly problem to you. Like this one. Alright, I'm almost there. Wish I would have had this bookmarked. But I didn't. Okay, so negative 2 minus 2i to the 5th power. And what am I feel like I'm doing something wrong. Maybe not. Maybe we just go with it. Okay, let's just go with it. Not all these are going to work out to be nice things anyway, so totally fine, I guess. And I'm sorry for that super long delay. So let's try to figure out 2 radical 2 raised to the 5th power. And I'm trying to still decide if I should have just left that as radical 8. But it's fine. So when I go to raise this to the 5th power, I have to raise this to the 5th power. So that's going to be 2 to the 5th. And then I have the radical 2 to the 5th power. Now remember, that's 2 to the 1/2 to the 5th power. So 2 to the 5 halves. Yeah, see now it's like I should have just left the 8. Oh, this is hurting my brain. Probably hurting your brain too. So then we have this cis over here. This is an easy product, so let's deal with that. 5 times 225, which is going to be 1,125 degrees. What in the world? Am I really just not seeing something? I swear it's just too late at night for me to be doing this. Probably too late at night for you too. Or maybe it's too early in the morning when you come to class and have to deal with this, right? Alright, let's keep going. So 2 to the 5th is going to be 32. And then this becomes 2 to the 2.5, 2 to the 5 halves power. That's the square root of 2 to the 5th. The square root of 32. Not really helpful. Maybe it's just going to work out. So I'm racking my brain here because I'm like, why does this look so bad? But maybe it will work out. So the 2 to the 5 halves power is going to be the square root of 2 to the 5th power, and 2 to the 5th power is 32. So the 2 to the 5 halves becomes a radical 32. 32 radical 32. Okay, keep going with it. I'm sorry, I keep stopping. And then I'm going to, again, expand this out. So we're looking at cosine of 1,125 plus I times the sine of 1,125. And we need to evaluate this because we're asked for the rectangular form. So let's take our 1,125 and again find a coterminal angle that's explicitly on the unit circle. So I'm just going to subtract out 360 a few times until I'm in that 0 to 360 range. So this is 45 degrees. That's good. So maybe this is going to work out. So this is really the same as 45 degrees. It's a coterminal angle, same exact spot. So we're looking at 32 radical. No, I can't write. 32 radical 32. And we have to multiply by the cosine at 45. That's easy. That's going to be a radical 2 over 2. Plus I times the sine is exactly the same at radical 2 over 2. Yeah, so maybe this does work out. It does. Oh my gosh. Like I was racking my brain thinking I did something wrong, but it totally works out. Okay. So when I go to evaluate this, continue evaluating, I gotta distribute, right? I'm gonna multiply here. When I multiply here, outside of the radicals, I have the 32 divided by the 2, which is going to make 16. And then I have the square root of inside the radicals, 32 times 2, which is 64. And the square root of 64 is 8. And 16 times 8 is 128. So I end up with 128. My goodness. Plus, this product here is going to be exactly the same. Oops, that's not what I wanted. This product here is going to be exactly the same thing, just with the imaginary. So that's going to get me 128i, and we did it. Hopefully nothing that ridiculous in your homework, huh? I'm sorry, I paused. I was totally thinking I did something wrong because this was ugly, but that is the way this works out. So if you stuck it out all the way to the end, again, my apologies that you had to hear all that. I hope you have enough to get going on your homework. As always, though, reach out if you have any questions. Until next time, take care.